Okay, so that's how materials basically behave. And now we're going to talk a little bit about biological materials. I know you guys care about bones and stuff. So this is for you, and I know you're thinking you really don't have to. We're going to. So now you understand sort of engineering version of how these materials work. Right? If they have a high modulus, they're really stiff. If they have a weak modulus, they're not so stiff. You push them too hard, they'll go plastic and break. So let's think about a material that you care about, which is, let's see, so biological materials. So biology is smart, they combine properties. And I would say it's a composite material, but I don't think anything biology really quite is technically a composite. And the thing I'm going to show you is more macroscopic. Why does the plastic connect to strain? That gets into the detailed material microscopic properties of the material. So that's now material science. As to why it has to do with like grain boundaries slipping past each other and all kinds of stuff. So they combine properties. So let's look at something. So I'm not just helping you with the physics part of the MCAT. Now we're into the medical part. And this will be very technical discussion. Let's look at a bone. Okay. So there's two kinds of material in a bone. You may have to memorize it. Maybe you already have. There's cortical and cancellous. Have y'all learned this before? I just learned this on Wikipedia an hour before. I learned it an hour before last year. So cortical is like the outside of the bone, right? So that's the strong part with all the hydroxyapatite, and that's what you think of as the bone. Cancellous is the spongy part on the inside. And what does it make? Blood cells or something? White blood cells. So you have two kinds of material that have to make up the bone for other reasons. And the question is, how do you want to arrange them in the bone? You put one on the inside, one on the outside. You want really strong bones. You don't want them to weigh too much. You want it to be easy to make. You're still got to make blood cells in them somewhere. So all these decisions have to be made by evolution. And if you think about it, if you're just thinking about tensile strength, it probably doesn't matter. Right? If there's tensile strength, then the cross-section of the bone could look like this. Here's cortical. Crap, they're both C's. Okay. Here's cancellous is the spongy one. Cortical is the rigid one. There you go. Spongy and rigid. They could be side by side for tensile strength, right? Because you're just pulling them side by side. But you also care about lateral compression. So let's take a second. What happens when you compress, when you push something to the side? Right? This is now like shear. Okay? Shear stress. Okay, compressive stress, we kind of talked about torsional stress. This is shear. And if you just look up shear stress, they're going to say it does this. Right? Which it doesn't really do. Okay? Mathematically, that is shear stress. But if you push on something, what actually happens before that is that you'll kind of bend it. This. That. When you bend it, what's really happening is you're getting compression on this side, and you're getting, extension on this side. On this side, there's some part in the middle that does nothing technically. It's the same length that it was. That's what really happens when you stress something from the side, like a bone. Okay? When you look at that, you might say, well, where then do we want to put the stiff part of the bone? On the outside. Right? We want all the stiff part to be here. We want stiff, or whatever, the high index or the high modulus on outside, where it actually has to compress, and you want the soft on the inside. That's why the cross section of your bone looks like this. Right? That's why this is the cortical, and this is the cancellous, or the spongy, or whatever it's called. But you can totally understand it from a simple Young's modulus. It just has to do with the Young's modulus of the two materials. It's the only thing that matters. Okay? And then, if you're going to be a bioengineer and think about how to use this stuff, you can think about helmets. Okay? So here's something interesting. Now I know how to win you over here. Let's go to the videotape here. This is a sure thing right there. This one's going to make fun of that. Okay, let's have time for that. Has anybody ever seen this video? This video makes me extremely angry. Okay? They don't walk like that. And they sure as hell don't cast a shadow. Come on, there's no way. There we go, we're doing hedgehogs. You guys are so easy. Okay, so if you think about how a helmet works here, what is a helmet good at? Right? A helmet is good at stopping a force this way, right? It's got the right compressive materials, we put the right Young's modulus in there, everything, and it's really great at absorbing all of the load that way to your head. But that's no good, right? So the reason people give, I've got 10 emails about what are they called? Concussions, right? Is you don't always get hit right on the straight on the head, you get hit to the side, and your brain gets like jerked around sideways. Your brain gets a torque. You hate torque, right? You hate that part of the class. That's also what causes a concussion. And helmets are no good at stopping torque. That's the problem. Is the helmet's great for straight on, but if you think about the helmet, it's just kind of sitting loose on your head. It's not designed to absorb impact to the side, right? But hedgehogs, okay? So here, now this, I don't think the hedgehog was launched. Okay, so here, the hedgehog's going to take a nasty spill. Right, here he goes. He's foraging for food. And he's 30 feet up or so. He's like, whoa, I lost my grip. Oh, the quills save the hedgehog, right? Because what the quills are doing is they're redirecting the forces. Right? Oh, that's how something else did. But you can imagine that what the quills do is they interact with each other, and as they push sideways, they push each other, and they manage to soften the lateral impact, the rotational impact of the thing, right? It redistributes it. So what people are working on is putting porcupine quills inside of the helmet, where the helmet literally would be kind of like loose. You know, if you got hit to the side, the helmet would take it and not the head. At least according to the company that is selling this. That is exactly how it's okay, so that's your biomaterials lecture. So I will see you on Thursday. We'll do practice problems on Thursday.